Okay, guys, I'm going to look at this paper. This is a May-June 2025. It's variant 2.1. So let's have a look at this paper, see if you can find some things useful. Okay, question 1, it says solid sodium conducts electricity. Sodium oxide conducts electricity when molten, but not when solid. So let's look at what we have here. Okay, let me pick my pen. So solid sodium. So we are talking about solid sodium. Sodium is a metal. And then they say it conducts electricity. Then we have sodium oxide, which also conducts electricity when molten, but not when solid. So this is an ionic compound. So metal and ionic compound. Name the type of bonding present in sodium and in sodium oxide. So we've just said it. Bonding in sodium is metallic. The bonding in sodium oxide is ionic. Okay. You can say metallic bonding or ionic bonding, it doesn't matter. Okay, so I'll leave that one like that. Explain how solid sodium conducts electricity. Solid sodium, so that's the metal, isn't it? Not the ionic compound. Okay, it has a sea of delocalized electrons. It has a sea of delocalized electrons that can carry electrical charge. Okay, explain why sodium oxide conducts electricity when molten. Because it has in molten state. It I don't have to say it. We can say in molten state, the ions, not electrons, but the ions are free to move and carry charge. The ions are mobile and carry electrical charge and can carry electrical charge. That's it. Okay, separate samples of sodium and sodium oxide are each added to an excess of cold water. Write an equation for the reaction of sodium with cold water. So this is a metal reacting with water. We know this reaction. When you take solid sodium metal and then you drop it on water, you know, it starts it melts and then it starts going in circles above the water with a flame, releasing hydrogen gas. So we're going to say sodium metal plus liquid water, which is cold water, of course. This will result in the formation of sodium hydroxide. The solution, you know that if you put litmus paper in there, you will see that it will be alkaline. So this one will be in aqueous, and then you can say plus hydrogen gas. Okay, so that's the reaction. Write an equation for the reaction of sodium oxide with cold water. This is the oxide of sodium, the ionic compound. This one is a basic oxide, okay? This is a basic oxide, so we can say sodium oxide reacting with water. This one, of course, just goes straight away and forms the alkaline solution. So that's sodium hydroxide. Yeah, we don't produce gas here. So I'll write this like that. Complete table 1.1. Do not refer to temperature changes when considering observations for these reactions. So you've been given an instruction, please do not refer to temperature changes. It doesn't matter. Let's think about something else. So we are comparing reactions of sodium and sodium oxide reacting with, okay, so one similarity in terms of the observation when it's added to cold water. So what is the similarity? Okay, so they both can form aqueous sodium hydroxide. But is this something that you're going to observe? You cannot observe it. And they didn't say carry out additional tests with the litmus paper. So what we will see is that both sodium metal and sodium oxide will dissolve in cold water to form an alkaline solution. Will dissolve. Okay, I'll just leave it like that. One difference in observation on addition to cold water. So something that we can see, we already said in our equations that sodium, when it reacts with water, it will form hydrogen gas. So sodium here, we are going to observe formation of gas, which is effervescence. Effervescence, how do you write effervescence again? I don't know. You can check this one, I forgot. Effervescence, and when we, okay, then here there's no effervescence. So what you're going to see is that you see effervescence that side, no effervescence on the other side. But what you actually just see, you can say no effervescence, clear solution formed. Okay, one difference. Okay, I'll just say no effervescence because that's one difference. But it will form a clear solution. Both of them will form a clear solution, isn't it? Effervescence, if that spelling is correct, I don't know. Okay, so like that, they don't mark the spelling. State the oxidation state, state the oxidation number of the period 3 element bonded to chlorine in sodium chloride and PCl5. Explain the difference in the oxidation number. In sodium chloride, sodium is an oxidation state of, is an oxidation number of, oxidation number of +1, and phosphorus is what is the oxidation state? The +1, +5, because it's +5 because we have 5 chlorines which are -1. Each chlorine is -1. So I have -1 times 5, and this must be balanced by 5 positives here. So it's +5 in PCl5. Okay, they say explain the difference. The difference is that, am I right there? Okay, I'm right. So the difference is that sodium loses 1 electron, or it has 1 electron in its valence shell, which is going to lose to chlorine. Phosphorus has 5 electrons in its outer shell. It doesn't lose them. It uses the electrons to form covalent bonds. And this is one of those situations where the octet rule is not obeyed, because how many electrons I'm going to have pairs? I'm going to have 10, so around the phosphorus. So we can say sodium is 1 electron, let me say valence electron to save space, is 1 valence electron, whereas phosphorus is 5. I think that's it. Table 1.2 shows melting points of oxides, of some oxides. Okay, oxides, we do have sulfur dioxide, water, and all that. Okay, they give us, we can see these ones, they're very high melting points. So what they want us to do, a student suggests the following hypothesis. The higher the oxidation number of the element combined with oxygen, the higher the melting point of the oxide. Okay. Use table 1.2 to deduce if this hypothesis is true or false, or if there is not enough information to make a conclusion. Explain your answer. Okay, so let's make use of the table, right? They say you should use the table. So the student said what? They said the higher the oxidation number of the element that is bonded to oxygen, then the higher the melting point. So let's test that. So for instance, should I use hydrogen? No, because I don't see anywhere else where hydrogen is. Oh, but we could say the oxidation state of hydrogen here is +1. And I could say the oxidation state of magnesium here is +2. In this case, it would appear then that the student is correct, because we can see that the higher the oxidation state, the higher the melting point. Okay, but let's compare with something else. So maybe if we compare magnesium and aluminium, so we can say that the oxidation state of aluminium here is +3, but we see that +3 has a lower melting point than +2. So magnesium is an oxidation state of +2, but its melting point is higher than that of aluminium oxide. So that's not true. The hypothesis is false. So we could use, again, if you want, you can compare. Let's compare the sulfurs here. Sulfur here is an oxidation state of +4. Sulfur here is an oxidation state of +6. So here it would appear as if the student is correct. But when we consider magnesium oxide and aluminium oxide, you can see that's not necessarily true. Yeah, and also, again, if you consider this one, if you consider silicon 4 oxide, the oxidation state here is +4. But we see, although it has got a high oxidation state, the silicon, the melting point is actually low. So not true. So I'll say false, right? Was they asked. So it's not false. Why? Because in silicon 4 oxide, silicon is an oxidation number, oxidation number of +4. But its melting point is lower than that of, say, for instance, magnesium oxide, where magnesium is an oxidation number of 2. Oxidation number of 2, of +2, not 2. Okay, like that. So clearly we could just refer to those, isn't it? So here I just chose to compare these two, these ones. So yeah, choose, you could compare the bottom two, whichever you compare. A sample of iron is analyzed using a mass spectrometer. The mass spectrum shows 3 isotopes of iron are present. I'm trying to think about them. Okay, the mass spectrum shows that 3 isotopes of iron are present in the sample. Define isotopes. Okay, these are, okay, let me think how I want to start my sentence. Define isotopes. Okay, let me say these. I want to say these. These are atoms of the same element, okay, of the same element, having the same proton number, the same number of protons, but with different nucleon numbers. You could say nucleon numbers, or you could say neutron numbers, or mass numbers, whatever you say. Okay. Figure 2.1 shows the mass spectrum of the sample of iron. Okay, that iron. They already told us that it has how many? 3 isotopes. So we can see the 3 isotopes here. All right, use figure 2.1 to calculate the relative atomic mass of iron to 1 decimal place. Please follow instructions here. We know that relative atomic mass is the abundance multiplied by the mass per charge ratio. So this is going to be 5.9 times 54.0, but I'm not going to put the 0.0, plus 56 multiplied by, what is the abundance there? That's 91.9. Okay, 91.9 plus 57 multiplied by 2.2. And all this divided by, you've got to add the abundances. So if you add those abundances, the 5.9 plus the 91.9 plus the 2.2. And I'm sure that pretty much should give us 100%. But anyways, put that in your calculator, get your answer, give it to 1 decimal place. Now I can't do fractions on this. Oh, I do have an on-screen calculator, roughly around the same mass per charge ratios we have in the question. Okay, let's see what this is now. 55.9. Okay, now that makes sense. So this is 55.9. Okay, so the mass is 55.9. Okay, what am I writing here? 55.9, that will be the mass. Please just make sure when you get your answer here, it must be close to the mass per charge ratios that you have used. Okay, and then we move on. It says complete table 2.1 to show the number of protons and nucleons in one atom. Be careful here. It says nucleons, not neutrons. in one atom of iron 56. Okay, iron with a mass of 56. How many nucleons is the mass number? So it's 56. But what is the number of position of iron on the periodic table? Iron is number 26, so that means it's got 26 protons, so it's number 26. Deduce the number of pairs of electrons in the shell with principal quantum number 3 in an iron atom. Okay, iron, what? Deduce the number of pairs of electrons in the shell with principal quantum number 3 in an atom of iron. Be careful. All right, this is not just the 3D, it's 3s, 3p, 3d. Okay, so iron, you can do the configuration. Iron, we said it's number 26 on the periodic table. I'm just looking at my periodic table on the wall here. So it's got 3s after neon. So I'm going to start from neon to do its configuration. So it's got a neon core, but we have to pass this, isn't it? But I'm going to say neon, which is 2p, right? And then I go 3s, 3s2, 3p6, and then after 3p, I have to go to 3d. But you don't feel the 3d first, so I'm going to say 3d, and then I'm going to say 4s here. So 4s2, and then 3d, we have how many electrons in the d orbital? We have 1, 2, 3, 4, 5, 6. 6 electrons in the d orbital. So it's like this. So this is an iron atom, not iron, of iron. All right, so they say deduce the number of pairs of electrons in the shell with this. So there's 1 here, and there is 3 here, and here is a d orbital. So it's going to have, we're going to singly put 5 singly first, and then you pair once. So there's only 1 pair in this. There's only 1. So altogether, it's 5 pairs in the 3D, or in the quantum energy level number 3. So in quantum energy level number 3, you have a pair in the S2 orbit, in the 3s, you have 3 pairs in the 3p, and when you put the 6 electrons in the 3d, only 1 is going to be paired up. So you have got 5 in total. Write an equation to represent the first ionization energy of iron. Okay, by definition, first ionization energy is the amount of energy that is required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element to form 1 mole of gaseous 1+ ions. So gaseous is important. So we say ion in gaseous state, please don't say solid, to form Fe plus, because this is first ionization energy, gaseous, and then plus the lost electron. Okay, that's the electron you removed. Okay, suggest how the value for the first ionization energy of iron with a mass of 54 compares to the first ionization energy of iron with a mass of 56. Explain your answer in terms of the factors that affect ionization energy. Okay, so these are isotopes. They are both iron. It's iron, iron 54, iron 56. So these are isotopes. So they do have the same proton number, and therefore they have the same, since they are neutral, they have the same number of electrons. It's not about the mass numbers. It's not about the 56 and the 54, because that 56 and 54, the difference is coming from the number of neutrons, which are not important in terms of ionization. So they have the same ionization, first ionization energies. So we can say it's the same. The value is the same. The value is the same. We can say they have the same, both iron 54 and iron 56 is the same number of protons, the same number of electrons first. Let me say same number of, oh no, not it has. I'm talking about 2 things here. You have the same number of protons and same nuclear strength, nuclear charge, same strength of the nuclear charge, or same nuclear charge. I want to say same nuclear charge, save space, same nuclear charge. It's a repetition already, actually. number of electrons is the same, therefore they have the same electronic configuration. So number of electrons is the same. Number of electrons is the same. So they have the same. They have the same electron configuration. The same electron configuration. Hence, the same amount, you must kind of, I feel you must say this because we are talking about ionization energy. The same amount of energy is required to remove the outer electron. The outermost electron. Okay, yeah, you can see wasted space repeating. When we talk about protons, you're talking about nuclear charge. When you talk about same number of electrons, you're talking about electron configuration. So if you don't waste space, you can kind of throw in there that the attraction of the outer electron to the nucleus will be the same. The strength will be the same. So you can kind of throw in that as well. Hexene reacts with the hydrogen gas to produce hexane. So from, alkene to alkane, this is hydrogenation. A nickel catalyst is used here, it's required. Figure 3.1 shows the distribution of energies of hydrogen molecules at temperature T. Sketch on figure 3.1 the shape of the cave for the same sample of hydrogen molecules, they are in gaseous state, when the temperature is increased. Okay, the sample gets water, so obviously we expect when you increase the temperature, you'll shift the proportion here. It goes like this. Okay, so that is the case. So here you can say higher temperature, whatever. They didn't say what it's increased to, so we can say at higher temperature. At a higher temperature, this is going to be the case. So I'll just write it like that. Notice that I deliberately I didn't reach this line because most of the molecules have now shifted to this region. So ideally, you expect that the area here must be the same as the increase here. Okay, so, oh no, I need my eraser. I need to erase that. Okay, so I'll do that. And then it says, explain why increasing the temperature increases the rate of reaction. Obviously, we know what causes the increase in rate of reaction. The kinetic energy is the kinetic energy of the particles, kinetic energies of reactant molecules. Increasing the frequency of collisions as molecules move faster. State the role of nickel when it is added to reaction 1. They didn't say, but we know that nickel is a catalyst that is used for hydrogenation. That we know. So we're just going to say it's a catalyst. It acts as a catalyst. You can say that. Annotate figure 3.2 to show the effect of adding nickel to reaction 1 at temperature T. So same temperature. So this current temperature, this distribution profile, keep it like as it is. But then we introduce a catalyst. What do catalysts do? They lower the activation energy. So I'll just do this, and then I'll say EA cat, right? Then we can say without nickel, with nickel. That's it. Define Le Chatelier's principle. again, I don't know whether you say Lee or Le Chatelier's principle. Define that. For me, I say what? I like to say it's an odd definition. I don't know if people have changed it, but it says that for a system at equilibrium, when subjected to a disturbance, the system will behave. The system will behave in such a way to counteract the disturbance. System will behave in such a way to counteract the disturbance. Reducing its effect. So if, let's say, you had increased temperature, the system will try to reduce it. Okay. Reaction 2 shows the equilibrium reaction between gas X and gas Y to produce gas Z or Z in a sealed container. And the stoichiometry is APC. Figure 3.3 shows the effect of changing pressure on the percentage yield of Z and two different temperatures. Okay, so we have temperature and we have pressure. All right. And then we have yield on the y-axis. We have pressure on the horizontal. So there's just two conclusions. So my conclusions obviously have to be about temperature and pressure. So we can see that when we decrease the temperature, you see 300 versus 350. When we decrease the temperature, the yield of Z increases. So what is that kind of reaction? When we reduce the temperature, we favor the forward reaction that produces Z. So the forward reaction must be exothermic because reducing the temperature must favor the reaction that produces Z. So the reaction that produces Z, which is the forward reaction, must be an exothermic one, such that when we reduce the temperature, then that reaction is favored. So I will conclude here that the forward reaction is exothermic. The forward reaction is exothermic as more Z is produced at lower temperature, as it is favored by a lower temperature. They didn't say we must explain, but look, I'm just explaining. Another thing that we see is that when you increase the pressure, because that way we're increasing the pressure, we see that the yield also goes up. So pressure and yield are directly proportional. So let's think about what we do when in equilibrium in class. Isn't it we say that when you increase the pressure, the reaction that produces fewer molecules of gas will be favored because we want to try and reduce the pressure. So the reaction will favor the one that reduces the number of molecules of gas. So if Z is favored by increasing the pressure, it means that the number of moles, the stoichiometry here, which is the C, it must be less. So C must be less than the total number of moles on the left. So A moles of gas plus B moles of gas must be higher than C, so that when I increase the pressure, the reaction will go to C because C is fewer molecules of gas. So I can conclude that the stoichiometry C is less than the total of, or the sum, let me say, or less than the sum of what A and B. Is it A and B? Of A and B, yeah. A and B. So I can also conclude that if you want to, the reason is that because increasing pressure favors the forward reaction, which must be fewer molecules of gas. Anyways, they didn't say we must explain. The structure of vitamin C is shown in figure 4.1. There is vitamin C. Deduce the empirical formula of vitamin C. This one is just counting, isn't it? How many carbons are in here? 1, 2, 3, 4, 5, 6. So I'm writing right now, I'm writing the molecular formula. So C6. And how many hydrogens? How many hydrogens? So let me deal with the hydrogens now. Okay, so I see there's, let's leave the ones that are written, count the ones that are not visible, because those ones are the tricky ones. So there is 1 here, there is 2 here, there's 3, 4 here. Then we say 5, 6, 7, 8. I don't see anywhere else, so I'll say 8. And then we go to oxygens. How many oxygens? Oxygens are always written, so you just count the ones that are present. 1, 2, 3, 4, 5, 6. So 6 here. So the empirical formula is going to be divided by 2 here. It's going to be C3, H4, O3. Okay, so C3, H4, O3. That will be my answer there. Okay. Right, moving on. Okay, the concentration of C is found by titration with iodine. So if we take vitamin C and then, I said of vitamin C, and we react it with iodine, there's a reaction that happens, and then the reaction is according to this equation here. A vitamin C tablet is dissolved in water to produce 200 cm3. Okay, 200 cm3 solution. And then from this 200, we took 5 of this solution. And then we added it to a flask that had water that was around 150 cm3. And then indicator was also present. All right, so we now have, I would say, approximately 155 volume total in this now, in this solution, approximately 155 volume. And this contains vitamin C, 5 cm3. And within this 5 cm3, there are some molecules of vitamin C, we'll find out. Exactly 28.4 cm3 of this concentration of iodine reacts with the sample of vitamin C solution in the flask. So we can say number of moles. What? Okay, let me read the question. What is the question? Calculate the amount in moles of iodine added to the flask in this titration. Okay, number of moles is equal to concentration times volume. So concentration is 5.00 times 10 to the minus 4, and then multiply this by 28.40, but divide this by 1,000 because look, its volume must be decimeter cube. So equal to, then I go to my on-screen calculator, and okay, let me put this calculator this side. Okay, so it's 5 exponent, no, not exponent. Yeah, it's exponent, isn't it? They say exponent, the button on the calculator. Exponent -4, and then I'll press equal sign because I'm cautious, I'm trying to be cautious. And then we say 28.4 divided by 1,000. You can just press everything and then say equal to. So it gives me 1.42 times 10 to the minus 5. 1.42 by 10 to the minus 5. Okay, so these are the moles. Okay, so 1.42 by 10 to the minus 5 moles. Okay, so concentration times volume. All right, now they say use your answer to B part 1 to calculate the mass in grams of vitamin C in the tablet. In that tablet, show your working. If you were unable to calculate, use this. Okay, we were able to calculate. So we now want what? What do we want? Use your answer to calculate the mass in grams of vitamin C in the tablet. So in the 200 cm3, you understand? So the stoichiometry of the equation is that 1 mole of iodine reacts with 1 mole of vitamin C. So that means if I reacted this number of moles of iodine, 1.42 times 10 to the minus 5, that would mean that in the 150 cm3 solution, whatever that was, there was the same number of moles. So there was 1.42 times 10 to the minus 5 moles of vitamin C. But these moles were in 5 cm3. You see, they came with 5 cm3. So now we therefore have to do proportionality to say if these moles came with the 5, how much were in 200? You understand? So we're going to say moles. So moles in, okay, let me my pen. So we're saying 5 cm cube, right, had 1.42 times 10 to the minus 5. Is it? Let me go back up. Yes, number of moles. These are moles. So how much were in 200? So this is the question you're asking. Then you say here, question mark. So basically what you're doing is going to be 200 multiplied by the number of moles divided by 5. Okay, so you're saying 200 divided by 5. 200 divided by 5 equal to 40. So that 40 must be multiplied by the number of moles, 1.42 exponent -5. And that gives me this number, 5.68 times 10 to the minus 4. 5.68 times 10 to the minus 4. These are moles. So we want mass of vitamin C. So mass is equal to number of moles times MR, isn't it? So this is going to be, you're going to multiply here by the molecular mass of vitamin C, which was given up there. I saw it, 176. So you're going to multiply this number of moles times 176. So this answer multiplied by 176, multiplied by 176, that gives us 0.099999999. They said, did they ask any significant figures, or we must think about significant figures? 3. Let's give to 3 significant figures. 3 significant figures will be 0.1000. Okay, what am I writing? I'm going to write 0.100. 3 significant figures. This is 3 significant figures, right? I'll leave my answer like that. Okay. And did I multiply by 40? I hope so. All right, deduce the role of iodine in the reaction. Okay, let's go back and see what iodine was doing there. So we had, it's not a catalyst. So what was it? Let's look at what happened to iodine. Iodine had an oxidation state of 0, and it went to -1. So that means iodine was reduced. So if iodine was reduced, it means it was an oxidizing agent. It means it oxidized the vitamin C. And indeed, it did. I can see here, we lost this hydrogen. So by the other definition of oxidation and reduction, vitamin C was oxidized because hydrogen was removed from it. So we can say iodine was an oxidizing agent. So it's an oxidizing agent. They just say deduce the role. They didn't ask for any reasons. It was an oxidizing agent. I gave you the reason. Hydrogen was removed from vitamin C. Also, the iodine decreased in oxidation state. Suggested 2 reasons why concentrated, acidified potassium manganate 6, why am I getting that? Potassium manganate 7 is not a suitable reagent for producing Q from vitamin C. Where's Q? Who talked about Q? Oh, Q is that one. Look, this question, I told you they like this question. These are harsh oxidizing conditions. They will break sigma and double bonds, sigma and pi bonds in a double bond. And then you get either carbon dioxide, or if you had hydrogens, you get a ketone. If you had alkyl groups, you get a carboxylic acid from an aldehyde that wouldn't have survived the harsh oxidizing conditions. So this will break double bonds. It will hydrolyze, you would say. This is hydrolysis. No, you're not adding water. It will break. Okay. That's the case here. So Q, but you can see Q is intact here. It still has its sigma bond here. That sigma bond was not broken. But those conditions that they are providing would break the sigma and the pi bond here. So this pi bond and this sigma bond will be broken, both of them. If we add cold dilute, then we get a diol. Okay, we get a diol, of which here I already had alcohols, but I don't know what will happen then. So here we can say, suggest 2 reasons why hot concentrated acidified potassium manganate is because is not suitable as a reagent. So how do I start my answer? I want to write exactly what I just said now. These conditions would, okay, I'll write like that. These conditions would break both the sigma and pi bonds of the C to C double bond. Like that. Suggests two reasons why what concentrated is not suitable as a reagent. Let's go and have a look again. Oxidizing agent. Notice what happened here. Can you see that this side is a primary alcohol because we have CH2OH. Here we still have CH2OH. So if I use those conditions, this primary alcohol will be oxidized to a carboxylic acid. This secondary alcohol would be oxidized to a ketone. But that's not what's happening. Okay, so I'm going to comment on that. So I'll say, secondly, the primary and secondary alcohol groups or alcohol functional groups would be oxidized. But we can see in Q, they were not oxidized. So I'll leave this one like that. Then say predict two absorptions that will be seen in the infrared of both vitamin C and compound Q. I like that they've given us the structures again here. Describe the relevant bond and the specific functional group that is responsible for each absorption identified. Predict two absorptions. Okay, we do have information down there, I see. Predict two absorptions that will be seen in the infrared spectra of both vitamin C and Q. Describe the relevant bond. Okay, so we need two. So number one, we are going to see the OH absorption peak. And the other one that we will see is this ester one here. See this one? This is an ester. It's a cyclic ester. And then we have the alcohols. So that's what I'm going to talk about. Yeah, this one is a ketone. This one doesn't have a ketone. So don't talk about the carbonyl group. We have to talk about the ester groups. So let's talk first about, let me read the question again. Predict two absorption peaks. So the absorption peak of the alcohol is this one, hydroxy. It's going to be 3000 to quote this wave number. You must quote that wave number. And the CO of an ester bond is this one. So you must quote this one as well. So we are going to refer to those. So we'll see an absorption peak, a C2O ester absorption peak would be seen. No, let me not say that. Let me say end, peak end. And I'm going to say end in OH. Okay, OH hydroxy. Is they say hydroxy? Yes, hydroxy. A C2O and absorption peaks. I don't like how I'm writing this. I'd rather write it like this. A C2O, which is the ester, and an OH, which is a hydroxy. Writing is tough, isn't it? Which is a hydroxy. Absorption peaks. Now there are more, so I'll say absorption peaks. Ooh, I'm tired. I'm tired. Why am I writing like that? Absorption peaks would be seen at wave numbers, at wave number ranges. I don't know. I started with carbonyl, right? So I'll say 1710 to 1750, and The hydrox one is 3,200 and 3,200 to 3,650, is it? To 3,650 respectively. Okay, why am I saying respectively? Because I started with the carbonyl first, and then I had the hydroxy. And then I'll say for both, if you will, both vitamin C and Q. For both vitamin C and Q. You will have space. You can shorten this, okay? You will have space because you use a pen. So I hope you'll be able to write a meaningful answer there. Okay, are we done? No, we're not. Okay, they say compound A contains the elements. How long have I been doing this? Compound A contains the, how long? I don't know. Compound A contains the elements carbon, hydrogen, and oxygen only. When A is heated with sulfuric acid aqueous, okay, we are heating. Compound B and C are produced as shown in this figure. Draw the structure of A. Let's see what is formed. Sulfuric acid is used as a dehydrating agent. But in this case, we are adding water. So this cannot be dehydration because we're adding water. So it's not hydrolysis, is it? No, it is hydrolysis, but it's not dehydration. Where, like in condensation, you can remove water and then make an ester bond, for instance. But in this case, we're actually adding. So this is acid hydrolysis because we took one thing, we added water, and then we split it. We split the carbons. We had a carbon. So you see now I have two carbon chains here. So I split it. So if I look at the structure, I see carboxylic acid, that's a dioic acid. And these here are two molecules of alcohol, ethanol, two, because there's stoichiometry of two here. So that means this dioic acid has then alcohol on one side and then alcohol on the other side. So there was acid hydrolysis. Good. So let's write here acid hydrolysis, If you say hydrolysis, it's up to you. Okay, so I can picture what this thing is because it's got C. They want to draw the structure. Okay, I'll draw it. So we have this C, and then there's the CH2 in the middle. So I'm going to put the CH2, and I'll put it like that. That's CH2. And then I'm going to put that other C. So you see there are three carbons on B. So that means the other one, double bond here. And then I'm going to do a double bond there. And then this would have gone to ethanol, not ethanoic acid. I want to say ethanoic acid. So it would have been like this. And this was also the case on the other side because I have two molecules of ethanol. So this was also the case this side before the acid hydrolysis. You see? So when we added the aqueous, the water in the presence of acid and heat, we then broke the ester bonds. Name the type of reaction that occurs when A is heated. I just mentioned it. It's acid hydrolysis. It's acid hydrolysis. Or if you say hydrolysis, it's up to you. Acid hydrolysis. So I can erase it here. I didn't know they were going to ask it, but they did. When aqueous sodium carbonate is added to separate samples of B and C, effervescence is observed with B only. What is B? Yeah, B is an acid, as we know. Dilute acids react, not dilute, any acid with a carbonate. You're going to see effervescence of carbon dioxide. C is an alcohol. Complete the equation to describe the reaction. No, when aqueous sodium carbonate, I tried that. Complete the equation to describe the reaction between B and an excess of aqueous sodium carbonate. Okay, so this will form. Okay, so right, this hydrogen will be replaced with sodium. This will be replaced with sodium because then now we have a carboxylate like that, negatives, and then I form COO minus N plus. So it's like kind of ionic there. So we can say Na plus, and then you can say O minus, if you will. You don't have to write those, do you? And O C A. No, I'm skipping something there. I'm realizing I missed a carbon, didn't I? This one, CH2, and then you're gonna have COO minus Na and a plus here. So maybe write this plus that side just to make it look better, plus and minus there. And then what happens is you're gonna have carbon dioxide, as we know that there's gonna be effervescence. There's going to be carbon dioxide, what else? And water, isn't it? Where did the hydrogens go? So, and the water. Like that. So they want us to balance the equation. So carbon dioxide. So it's a 1 here and a 1 there, isn't it? Yeah. So it will balance like that. It will balance like that. Let me check. These two hydrogens that we removed, they formed water. So we're good. And then everything is fine. We're good. I think we'll leave it like that. Suggest YC does not react with aqueous sodium carbonate in a similar type of reaction to B. Why does it not produce effervescence, carbon dioxide, and all that? Why does it not do that? Because it's an alcohol, it's ethanol. So ethanol, remember, what do you call it? Positive inductive effect and all that. Ethanol is like this, isn't it? CH3, CH2, OH. But let me draw it like this. So this pushes electrons, increasing the electron density on the oxygen. Therefore, this hydrogen is strongly attracted to that oxygen. So it doesn't want to go. So ethanol is very, very much not acidic. It's not acidic. It's not a good acid compared to carboxylic acid because the hydrogen is tightly held. So we can say ethanol, why suggest YC? Oh, they're calling it C. So don't say ethanol, they're calling it C. C is not a good acid. A good acid because of the positive inductive effect of the alkyl group. Okay. Because of the positive inductive effect of the alkyl group. What do we mean? It will mean that the O to H bond is strong. So hydrogen is not easily released. So it's not a good acid because it doesn't release hydrogen easily. A student suggests a two-step synthesis to produce compound B. Okay, B is that. It's shown in that figure. Identify the reagents and conditions required in steps 1 and 2. What's going on in step 1? We have a halogenoalkane. This is a di-halogenoalkane, 2 chlorines on both ends, converted to chlorine has been replaced with OH. That's a nucleophilic substitution reaction. We have substituted the chlorine because remember, on that carbon, there's hydrogen like that, and then there's chlorine here. So there's a polarity here, partial negative, partial positive. And then we need an OH, which is a nucleophile. That's going to attack there. Right, so we need a source of that nucleophile. So we are going to use sodium hydroxide. If we use sodium hydroxide in ethanolic conditions, then we get elimination. We introduce double bonds. So this must be aqueous sodium hydroxide under reflux. Under reflux. We can say heat under reflux. Heat under reflux. Why do you need to heat under reflux? Because of the halogen. What is it? The halogenoalkane. Those things they are volatile. So you don't want them to escape. So you heat under reflux, you achieve your substitution. Step 2, we have the alcohol being converted to a carboxylic acid. That means there's been oxidation there. So I need an oxidizing agent. Is that so? Yeah, I need an oxidizing agent. So what could I use? I could heat in concentrated potassium permanganate 7. Okay, heat. We did this before. So if I heat with concentrated potassium permanganate, you know this is a strong oxidizing agent. So heat with concentrated. Does it work when it's just concentrated like that? Heat with, I don't know if you even need to heat it, but heat with acidified, as you know in the label, always acidified. Acidified, concentrated. I don't know if it needs to be concentrated. I'm just going to give the maximum hash conditions, probably not necessary. Heat with acidified concentrated potassium permanganate 7. Aqueous potassium permanganate. It has to be aqueous again. As you know, in the label, we give you with this label, acidified concentrated aqueous potassium manganate. Km, that will be a capital M, MnO4, like that. All right, so that one, you can just say that. Identify the type of reaction that this diol undergoes in step 2, oxidation. It is being oxidized, oxidation. It's being oxidized to a carboxylic acid. Okay, next. Oh, this test is long, we're not done. B reacts with an excess of reducing agent R to produce D. What is B again? B is the dioic acid. Reacts with an excess of reducing agent to produce D. Okay, so you can reduce the carboxylic acid. So remember, B is a carboxylic acid. They're saying you can reduce it to produce D. So a carboxylic acid can be reduced to an aldehyde or a primer alcohol. But let's see. They say an excess of PCl5 is added to D. Okay, so that means maybe we had reduced it to an aldehyde or to a primer alcohol. If it was a primer alcohol, then I can add PCl5. The Cl of the PCl5 will substitute the OH. A vigorous reaction occurs and misty fumes are seen. Or is this one forming an, because if it was an aldehyde, you could form an acyl chloride, I guess. But I think this is a primer alcohol. And then you form misty fumes. This will be hydrogen, the hydrogen that came from the alcohol. And then you form hydrochloric acid. Organic compound E is produced. What's going on? They're saying, okay, I see. So D, which I suppose D was, remember, we had reduced with an excess of reducing agent. So I'm sure we didn't end because we had an excess. We didn't end at the aldehyde. We reduced again because of the excess to primer alcohol. Then the primer alcohol underwent substitution with PCl5, and then I had chlorines on either end. And then those chlorines on either end, they say a vigorous reaction occurs. Okay, yeah, we see. So identify the formula of the reducing agent R. So we can use a reducing agent, which is lithium tetrahydrid aluminate. So how do we write it? Is it, yeah, like so, isn't it? So that's a reducing agent. And then complete the equation to describe the reaction of B with an excess of R. So B reacting with R. So this reacting with that. So like I said, it's going to form a primer alcohol. So I'm going to say C, and that will be CH2 because it's now a primer alcohol. And this CH2 was present already. And then the other C also becomes CH2. And then I'll have OH. And here also OH. And then we removed oxygens, we removed, so we must produce water, isn't it? I guess. Let's see. We removed this hydrogen, that one, and then the oxygens. So I'm sure we'll produce water because of the oxygens. So produce water. All right, so I'll just produce water. Let's see. Now, think about the balancing this thing now. So we had one oxygen here was removed, one oxygen was removed. So I need to put a 2 here so that my oxygens are balanced. There are 4 on either side. So make sure you put a 2 on the water. Now, how many hydrogens did you add? So if you look at this, you added these 2 hydrogens, they were not there. You added these 2 hydrogens, they were not there, right? And then you added 4 hydrogens here. So 2, 4, 4, 8. So this one, I'll put an 8 and then put a 1 there. Okay, that's how I'll balance that equation. I hope you can check and see if it's balanced. Name organic compound E. Organic compound E is produced when what happens? When we react with PCl5, okay, that will be, how many carbon do I have? 1, 2, 3. So that's going to be 1.3. 1.3 dichloro, because the chlorines will replace the OHs. So one at the one end and the other one on the other end. So 1.3 dichloropropane. 1, 2, 3, yeah, propane. Okay, that's that. And oh, we have question 6 to go. 3 bottles of colorless liquids labeled F, G, and H contain separate pure samples of the compounds ethanol, propanol, and propanone, but not necessarily in that order. State the functional group in ethanol, propanol, and propanone. Okay, ketones and aldehydes, you have the carbonyl group, carbonyl functional group. Okay. State a reagent and the relevant observation that confirm that F, G, and H have the same functional group. Ketones and aldehydes give a positive test with 2.4 dinitrophenohydrazine. You can just write D and PH for dinitrophenohydrazine. The observation is that you get a deep orange precipitate. Deep orange precipitate. You remember this image of the test tube in your book. Deep orange precipitate. Precipitate is observed. Okay, separate samples of F, G, and H are each tested with tolerance reagent and with, I like this. This one confirms aldehydes. This one confirms not only methyl ketones, but it's mostly used for methyl ketones. But remember, if you have an aldehyde that can form a methyl ketone, that will work. If you have that can form, like if you have a secondary alcohol that has a methyl on one end, it will work. If you have an aldehyde that has a methyl on one end, it will work. So the table here, tolerance reagent alkaline, F gave with tolerance test is for aldehydes. So no observable change. So F is the ketone. And what was our ketone again? Confirmed, because it gave a pale yellow, so it has to be a methyl ketone. What was our ketone? Propanone. So that makes sense because propanone is like this, so it's a methyl ketone. So this one, F, would have been propanone. These two, because we had two aldehydes, ethanol and propanol, so both of them gave a positive silver mirror test. So that makes sense. But ethanol is like this. Ethanol. What am I doing? Sorry. Ethanol is like this. This is ethanol. And propanol is like this. Sorry, like that. So that's propanol. You can see 2 carbons and 3 carbons. So propanol, propanol, which is at the bottom, doesn't have a methyl this side, but it's got an ethyl. And then ethanol is a methyl this side. So this one is the one that should give a positive test for the iodoform. So G is ethanol. And the one that didn't give a precipitate, that will be propanol. Okay. I hope you understand that. And then it says, identify the yellow precipitate produced when this is added. That is triiodomethane. We know that because it's called the triiodomethane reaction. Triiodo. That's not how you write it, isn't it? Triiodomethane. If you can't spell this, just say C with H and I3 because it's triiodomethane. Compound J does not contain, wait, is J coming in? Or it's a different one. Compound J does not contain the same functional group as these guys. Compound J also reacts with this one to produce, remember I told you that secondary alcohols will also do the same thing, to produce a pale yellow precipitate. Suggests the structure of compound J. The compound J is a secondary alcohol with methyl on one side. So it can be something like this one. Okay, something like this one. Yeah, because if you oxidize it, it's going to become a ketone, a methyl ketone. So I can give this as an example. Oh, that's the end, actually. That's the end of the test. So we end here. At least, okay.